The stars feel eternal. They hang in the night sky like quiet gods, constant and unreachable. But even stars die, and when they do, they don't just fade out gently. They collapse, explode, devour, and transform. Some end in silence. Others go out with the violence of a billion nuclear bombs. Tonight, as the earth spins softly through the dark, let's drift slowly into the life and death of a star. This isn't a science lecture, this is a cosmic story, one of energy, pressure, balance, betrayal, and rebirth. So close your eyes, or don't, and follow the path of stardust from glowing birth to ultimate extinction. Part 1. Birth, the nursery of stars. Every star begins in a place so dark and cold it would seem lifeless to us. These are molecular clouds, giant stellar nurseries spanning light years across, invisible to the human eye, but teeming with potential. They're filled with hydrogen gas, helium, and cosmic dust, remnants from earlier generations of stars that lived and died long before our sun was even an idea. These clouds are stable for a long time, chilling quietly in the void. But stability is an illusion. A single event, like a shockwave from a nearby supernova, or even just the slow tug of gravity, can set off a chain reaction. That moment of instability, that's when birth begins. Gravity finds its grip, pulling clumps of gas together. A fragment of the cloud begins to collapse. As it shrinks, it heats up, violently. This is the beginning of a protostar. It's not yet a true star, but a chaotic embryo wrapped in darkness. The physics gets brutal. Gravity squeezes tighter and tighter, and the more it squeezes, the hotter the core becomes. Temperatures climb to tens of thousands, then hundreds of thousands of degrees Kelvin. Disks of matter form around the core, spinning like whirlpools. Magnetic fields twist, and often powerful jets of plasma erupt from the poles, stellar tantrums, blasting material back into the void. Even now, light is trapped. The gas is still too dense for it to escape. The protostar glows, but like a secret buried inside a cocoon. Astronomers spot these newborns in infrared, not visible light, because they're swaddled in dust. As pressure builds in the core, the atoms are forced into extreme proximity. Eventually, hydrogen nuclei, protons, are slammed together with such force that they fuse. This is nuclear fusion, the engine of the universe. 4 hydrogen atoms fuse into 1 helium atom. The mass difference is released as pure energy. Fusion ignites. A star is born. Now, fusion fights gravity. The energy radiating outward pushes against the pull inward. And finally, there's balance. This is called hydrostatic equilibrium. It's the star's first breath of stability. The powerful stellar winds that now flow outward from the new star blow away the remaining dust and gas. The star emerges from the cloud like a newborn from the womb, fiery, radiant, ready to burn for millions or billions of years. But stars rarely form in isolation. Most are born in clusters, groups of hundreds or thousands of stars all forming together. They may form planetary systems, orbit each other as binaries, or drift apart over eons. But they begin together, like siblings. The type of star depends on how much mass it gathers. A small, cool red dwarf might never shine brightly, but it could burn for trillions of years. A massive blue-white giant burns violently, living fast and dying young. Our sun, somewhere in the middle, ordinary but capable of extraordinary things. And here's the part that hits hardest. You are made of this. Carbon in your cells, iron in your blood, calcium in your bones. It all came from stars. Not just from their lives, but from their deaths. Every element heavier than hydrogen and helium was created inside stars, then scattered into space when they died. You are quite literally stardust. So next time you look at the night sky, don't just see stars, see the ancient past, see potential futures, see the atoms that once drifted through a nebula, now composing the person staring back at them. And know this, the stars are not eternal, but in their death they create new life, and in their birth they carry the seeds of everything. Part 2, the main sequence, the long balance. The star is born, but birth is just the beginning. Most of a star's life is spent on what astronomers call the main sequence, a long, stable period where it fuses hydrogen into helium in its core. This phase can last billions of years, and for our sun, it already has. Roughly halfway through, in fact. During the main sequence, a star is at peace. It has found its balance, like a tightrope walker frozen mid-step. Gravity wants to crush the star inward, but the energy from fusion pushes outward with equal force. This equilibrium holds the star together in a delicate harmony. Inside, the core is a seething nuclear furnace. Temperatures reach 15 million Kelvin or more. Hydrogen atoms are smashed together under immense pressure, fusing into helium and releasing photons, packets of light and energy. But those photons don't immediately escape. In the sun, it can take hundreds of thousands of years for a single photon to reach the surface. It bounces, scatters, and struggles through the dense plasma like a moth caught in fog. Eventually, the energy reaches the star's outer layers and radiates into space as the visible light we see. The surface temperature, color, and brightness depend on the star's mass. Cooler, smaller stars appear red or orange. Medium-mass stars, like the sun, shine yellow-white. Massive stars burn blue, hot, bright, and short-lived. But inside all of them, the story is the same. Hydrogen in, helium out, energy in, light out, pressure in, gravity out. Constant balance, but it won't last forever. Over time, the core's hydrogen runs out. The star is still massive, still burning, still shining, but its fuel is fading. It's like a candle still glowing brightly, even though the wax beneath is almost gone. The end is coming, even if the surface doesn't know it yet. Larger stars burn through their hydrogen much faster than smaller ones. That's the irony. The bigger and more powerful a star is, the shorter its life. A massive O-type star might live only a few million years. A tiny red dwarf? It could burn for 1 trillion. In this way, time is warped by size. A human might see the sun as eternal, but in stellar terms, it's middle-aged, and every second in its core, 600 million tons of hydrogen are fused into helium. Every second, 4 million tons of matter are lost as energy. E equals mc squared in action. Still, for now, the star is stable, calm, glowing, a giver of light and warmth, a silent guardian of any planets that happen to orbit nearby. For those planets, this phase is everything. Life, if it ever arises, depends on this long period of calm. Civilization depends on it. It's the heartbeat of the solar system. And then, one day, whether after 1 billion years or 1 trillion, that heartbeat starts to falter. The hydrogen in the core runs low, the balance begins to tip, and the star, which has shone steadily for eons, begins to change. Part 3, Red Giant, the Slow Death. The end begins quietly, not with an explosion, but with a shift. The hydrogen in the core is nearly gone. Fusion slows, pressure falters, and gravity, always waiting, begins to win. With no more hydrogen to fuse, the core contracts. It collapses in on itself, growing smaller and hotter. At the same time, the outer layers of the star, freed from the push of fusion, begin to expand. Massive expansion. The star swells to hundreds of times its original size. It engulfs the inner planets. If the sun becomes a red giant, Mercury and Venus will be consumed. Earth? Possibly. At best, it will be scorched. At worst, swallowed whole. As the core shrinks, the temperature rises until it hits a new threshold, one that ignites helium fusion. This is called the helium flash. It happens in a blink, releasing a staggering amount of energy. The star stabilizes again, briefly, fusing helium into carbon and oxygen. But this new fusion stage is shorter and less stable. Helium runs out far faster than hydrogen ever did, and when that happens, the star enters its final chaotic phases. For massive stars, fusion continues beyond helium. They begin to fuse heavier and heavier elements: carbon, neon, oxygen, silicon, each layer like an onion, each stage shorter than the last, a race toward iron. But for stars like the Sun, fusion ends with helium. The core becomes a dense ball of carbon and oxygen. The outer layers, unstable and loosely bound, begin to drift away into space, forming a glowing shell of gas known as a planetary nebula. It's a poetic end. A dying breath painted in ultraviolet light, a cosmic flower blooming in silence, and at its center, the leftover core remains, a white dwarf, hot and dense, but slowly cooling over billions of years. In the case of more massive stars, the core keeps collapsing, but iron is a dead end. It can't fuse into heavier elements without consuming energy. Fusion halts, pressure drops, gravity takes over completely, and that's when things get violent. Part 4, Supernova and Collapse. This is where the death of a star goes from tragic to apocalyptic. A supernova isn't just the end of a massive star. It's one of the most violent and important events in the universe. A single supernova can outshine an entire galaxy for weeks, releasing more energy in 10 seconds than our sun will emit in its entire lifetime. Let's rewind a moment. When a massive star, at least 8 times the mass of our sun, burns through its nuclear fuel, it forms an iron core. But here's the cosmic catch. Iron fusion doesn't produce energy. It costs energy. Once iron builds up, fusion stops. And in that moment, the star's internal furnace shuts down. There's no more outward pressure to resist gravity. Gravity doesn't hesitate. The core collapses in milliseconds. We're talking matter crashing inward at a quarter of the speed of light. Protons and electrons are crushed into neutrons. The core becomes a hyperdense ball of neutron matter, harder than anything we can imagine. This collapse halts abruptly, and like a rubber band snapping back, it rebounds. The outer layers, still falling inward, slam into this rebounding core. The result? A shockwave so intense it tears the star apart from the inside. That's the supernova. The shockwave blasts through the star's outer layers, ejecting them into space at thousands of kilometers per second. For a brief time, the star becomes so bright it can be seen in daylight from Earth. Ancient astronomers wrote about these guest stars, sudden new lights that appeared in the sky, lingered for weeks, and then vanished. We now know they were witnessing supernovae. What's left behind depends on the mass of the original star. If the core is between about 1.4 and 3 solar masses, it becomes a neutron star. Imagine the mass of the sun packed into a sphere just 20 kilometers across. It's so dense that a single teaspoon of neutron star material would weigh 1 billion tons. Some of these spin rapidly, shooting beams of radiation from their poles. We call those pulsars. But if the core is even heavier, gravity doesn't stop with a neutron star. It keeps collapsing, further, deeper, into an abyss of its own making, past the point where even light can escape. That's a black hole, the final, unstoppable outcome of stellar death. Black holes are the ultimate mystery. They warp space and time. They erase information. They bend the rules of physics as we understand them, and they often remain invisible, revealed only by the way they warp light and devour nearby matter. Yet from this destruction comes creation. The elements forged in the supernova, gold, silver, uranium, are scattered across the cosmos. These heavy elements don't form in ordinary fusion. They're born in the fire of a dying star. You wear them, you walk on them. Planets, moons, and even life depend on these scattered ashes. So the death of a star, as violent and final as it seems, is also a beginning. The explosion enriches the galaxy. It stirs clouds of gas. It seeds the next generation of stars and planets. Death makes life possible. And somewhere, maybe right now, in some distant corner of the universe, another star has just reached its limit. Its core collapses. The sky flashes. The shockwave begins. A star dies. A galaxy blinks. And the story goes on. Part 5. White dwarfs and neutron stars. Not every star ends in a cosmic explosion. In fact, most don't. Only the biggest stars die as supernovae. The rest fade out more quietly, but no less strangely. Let's talk about white dwarfs and neutron stars, two of the weirdest corpses in the universe. Let's start with stars like our sun. When a sun-sized star runs out of fuel, it doesn't explode. It puffs up into a red giant, shedding its outer layers gently over thousands of years. These layers drift off into space and form what's called a planetary nebula, a glowing shell of ionized gas. It's hauntingly beautiful and completely silent. What remains behind is the exposed core, a white-hot ball of carbon and oxygen. This is a white dwarf. Now, here's where things get wild. A white dwarf has no more fusion going on. It's not producing energy, but it doesn't collapse either. Why? Because of something called electron degeneracy pressure. It's a quantum effect. Basically, electrons hate being in the same place at the same time. This creates a pressure strong enough to hold up the entire star. White dwarfs are small, about the size of Earth, but they are absurdly dense. A teaspoon of white dwarf material would weigh tons, and they shine, not because they're burning anything, but because they're still hot. It takes billions of years for them to cool. Over unimaginable stretches of time, they'll fade into black dwarfs, dead, dark, and cold. But the universe isn't old enough yet for any black dwarfs to exist. They're theoretical. We've never seen one. We never will. Now, if you remember from segment 4, stars more massive than the sun can leave behind neutron stars after a supernova. These are even stranger. A neutron star is what happens when a core collapses and protons and electrons are crushed together to form neutrons. The result? A city-sized object with more mass than the sun. The gravity is so intense it warps space. Time itself slows near its surface. And these stars can spin fast. Some neutron stars rotate hundreds of times per second. Their magnetic fields are trillions of times stronger than Earth's. As they spin, they shoot out beams of radiation. When those beams sweep across Earth, we see a pulse of light. That's why we call them pulsars. They're like cosmic lighthouses. Now imagine this. You're standing on the surface of a neutron star. If you could survive, which you can't, you drop a marble. It hits the ground with the force of a nuclear bomb. That's the kind of gravity we're talking about. These stars, white dwarfs, and neutron stars are the leftovers. They're not flashy. They don't explode. But they represent the quiet, persistent reality of the cosmos. Everything ends. Even the brightest stars eventually burn out. But in their ashes, something remains, and for a long, long time, these stellar remnants drift through space, cold, quiet, forgotten, until something, maybe gravity, maybe chance, pulls them back into the cosmic dance. They are the ghosts of stars, and they're out there, still glowing in the dark. Part 6. Black Holes and the Final Fade. We've reached the darkest chapter, literally. Black holes, the cosmic reapers, the ultimate endpoints of the most massive stars, where gravity doesn't just win, it dominates so thoroughly that the laws of physics throw up their hands and say, I got nothing. When a truly massive star collapses, and its core surpasses the mass that even neutron degeneracy pressure can hold back, something terrifying happens. The collapse doesn't stop. It keeps going, squeezing matter into a point of infinite density, a singularity. Around it, space folds in on itself, forming a boundary called the event horizon. Cross it, and not even light escapes. To the outside universe, the black hole is invisible, an absence, but it leaves fingerprints, stars caught in weird orbits, jets of X-rays blasting from the edges, ripples in space-time itself, gravitational waves, detected by instruments here on Earth. These waves are born when black holes collide, sending shock waves across the universe like cosmic earthquakes. Black holes come in different sizes. Stellar mass black holes, just a few times the mass of our Sun, lurk throughout galaxies. Supermassive black holes, millions or billions of times more massive, anchor the hearts of galaxies, including our own Milky Way. And somewhere in between, there may be intermediate black holes, but they're elusive, like the cosmic Bigfoot. Now here's where it gets eerie. From the outside, time near a black hole slows down. To a distant observer, someone falling in appears frozen at the edge, redshifting into darkness. But from the inside, no one knows. Our equations break down. Space and time themselves twist into a singular point. We don't know what happens there. We might never know. But black holes aren't eternal tyrants. They evaporate, slowly. Through a process called Hawking radiation, black holes lose mass over trillions of years. It's a trickle, an almost imperceptible leak of energy. But eventually, even the mightiest black hole will vanish into nothing. A final sigh, a cosmic whisper. And then comes the fade. Picture the far future. The universe is cold, stars are gone. White dwarfs have turned black. Neutron stars have cooled to shadows. Black holes, the last titans, are shrinking. One by one, they wink out. This is the heat death of the universe, a state of maximum entropy where nothing interesting happens. No light, no life, no movement. Just an infinite frozen stillness. But maybe, just maybe, it's not the end. Some theories suggest new universes could bud off from black holes. That time itself may loop or bubble. That quantum fluctuations could reignite creation. For now, though, we end here, at the cold edge of time, a place shaped by stellar deaths, illuminated by their brief, brilliant lives, and darkened by the shadows they leave behind. The story of a star doesn't end in darkness. It ends in transformation, from light to dust to silence, and maybe, someday, back to light again. Part 7. Stellar Remnants and Galactic Recycling. When a star dies, it doesn't just vanish, it leaves behind clues. Remnants, ghosts of its former brilliance. These leftovers don't drift aimlessly through space. They become the building blocks for new cosmic generations. In death, stars plant the seeds for life. Let's take a closer look at what they leave behind. White dwarfs, neutron stars, black holes, and nebulas. These aren't just corpses, they're part of a galactic recycling program that's been running for billions of years. Remember planetary nebulas? Those luminous shells shed by sun-like stars? They don't last forever. Over tens of thousands of years, they fade and disperse, but the gas and dust they eject become part of the interstellar medium, the vast sea of raw material floating between stars. It's from this stuff that new stars and planets are born. And the heavy elements, those come from supernovae, iron, nickel, gold, uranium. These don't form in normal stars. They're created in the heat and pressure of a star's final moments. When those materials explode outward, they enrich nearby gas clouds. It's no exaggeration to say, you are made of star stuff. Every atom of calcium in your bones, every molecule of iron in your blood, was forged in the death throes of a star. Sometimes stellar remnants interact with their environment in dramatic ways. A neutron star can pull gas from a companion star, heating it until it glows with X-rays. A black hole may tear apart a passing star, devouring it piece by piece while emitting brilliant flares. These processes don't just illuminate the universe, they reveal the secrets of gravity, time, and energy. Even more incredible, these dramatic deaths kickstart life elsewhere. shock waves from supernovae compress nearby gas clouds, triggering the birth of new stars. In some cases, they even jumpstart the creation of solar systems. Our sun may have been born from one such cloud, triggered by a long-dead star's explosion. So stars don't just burn out, they pass the torch. One generation's ashes become the foundation for the next. It's a kind of cosmic reincarnation, a cycle of brilliance and silence, light and shadow, death, rebirth, and everything in between. And it means that even the coldest, loneliest corner of space may one day be warmed by the fire of a new star. Galactic recycling isn't just poetic, it's essential. Without it, galaxies would go dark, planets wouldn't exist, life couldn't form, the universe would be sterile, a graveyard without renewal. But because of stellar remnants, we have color and complexity. We have galaxies bursting with energy. We have the possibility of worlds and wonder. So the next time you look at the night sky, know this. You're seeing echoes, fragments, stardust, pieces of stars long dead, and stars yet to be born. Part 8, The Afterlife of Stars, Philosophical Reflections and Final Thoughts. We've walked through the life and death of stars, their birth, their blazing youth, their fiery ends. But now, in this final segment, we pull back. We reflect. What does all this really mean? The death of a star isn't just a scientific event, it's a story, a cosmic parable. And if you're listening to this as you drift to sleep, maybe the most important thing to carry with you isn't data, it's perspective. Stars live for millions, even billions of years. They shine with a power we can't truly grasp, but eventually, even they run out of fuel. Even they reach an end. And yet, in that ending, they give. They explode, they collapse, they scatter their atoms across galaxies. If you've ever felt afraid of endings, remember this. Every atom in your body came from a dying star. You are literally made of things that ended and then became something else. There's a humility in that, a quiet reassurance. The universe is built on cycles. Nothing lasts forever, not stars, not galaxies, not even time itself. But nothing is wasted either. Every death is a contribution, a step toward the next phase. When we talk about black holes, neutron stars, white dwarfs, we're not just talking about physics, we're talking about memory, legacy. The universe remembers its stars not with gravestones, but with light, motion, and matter. And while we sleep, while we dream, those processes continue. Somewhere, a star is collapsing. Somewhere else, a new one is forming from its ashes. The galaxy doesn't stop spinning. So maybe in some poetic way, we're all part of a great stellar rhythm, a cosmic heartbeat. You, me, the stars, the dust, the silence. When you next look at the sky, maybe you won't just see stars. Maybe you'll see stories, beginnings and ends. And maybe that quiet light in the dark will remind you nothing truly disappears. It only changes form. The stars die. But the universe goes on, and so do we.